Alright, so to start off the topic, we looked at scalar and vector quantities. So scalar are magnitude only versus vector, which have both magnitude and direction. So examples of scalar quantities include things like time, mass, distance, speed, which is distance over time, temperature, versus things like let's say displacement, similar to distance, velocity, similar to speed. However, we're talking about displacement over time as opposed to speed. We've got acceleration, which is change in velocity over time. Force. Another one would be momentum. Where does energy fall? Scalar or vector? Scalar is correct, yep. So you've got energy. However, what we notice is when we calculate energy, it's actually got vector quantities in it. So think about elastic potential energy, for example. You've got force times the displacement of the spring. So you've got two vectors multiplied together, producing a scalar quantity. You'll notice in each of these we've got one vector quantity, force, which is ma. So you've only got the one vector quantity within it. So once you start multiplying, then we lose that vector condition. All right. From there, we looked at kinematic graphs. Particularly focusing on two, which were displacement time and velocity time. There are similarities between the two. They're certainly related, and then we've got acceleration time and force time that we can link in, but predominantly this is what your exam will focus on. We'll touch on acceleration time in a second as well. So displacement time. Your gradient gives you your velocity. When it is horizontal, then there is no motion. If it's negative gradient, then it's travelling backwards relative to your direction that you've defined as your positive direction. And the t-axis is your point of reference. For velocity time graph, when you get your gradient, that's going to be change in v over change in t, which is our acceleration equation. So your gradient gives you your acceleration. When it's horizontal, that gives us, or tells us that it's moving at constant motion or constant velocity. Negative gradient tells us it's slowing down. And when it hits the t-axis, then that tells us that the object has no velocity. So it's now stationary. Really important when you're looking at these graphs in your exam that you focus on the right style of graph. If you have trouble remembering which set of criteria to apply, whack that little table there down on your cheat sheet. Okay? It takes up very little room as a really quick reference so that you don't just throw away 4 marks, 5 marks, possibly more, about questions on a graph. All right, the equations of motion. Equations of motion. We looked at 3 real key equations of motion. This is when A is constant. So for any scenario where you've got constant acceleration, these are the equations that you're going to use, which leads us into projectile motion, but not just projectile motion. So you've got V equals U plus AT. Often that's rewritten as A equals V minus U over T. We've got X equals UT plus a half AT squared, and V squared equals U squared plus 2AX. Okay, just want to reiterate when we're getting a problem, the steps that we want to take. Solve a problem. First thing that you want to do, if you don't have one, is draw a diagram. Label your diagram, add all the bits, which leads into list the variables. Listing the variables where you write down what you've got and the one that you're after often tells us which equation that we want. Pick the equation for substitute and solve. Okay, when we substitute, check your units. Make sure you've got consistency in your units. We're in meters for everything. We're in seconds for everything. Or meters per second squared, rather than a time in minutes or something like that. So you've got to have unit consistency. Okay, so projectiles. This is where we started to look at 2-dimensional motion. And we've got a couple of ways that we can, a couple of styles of question, I suppose. So the first one is horizontal projection. In this scenario, your object is launched horizontally and then follows a half parabola or parabolic path down to its point of impact. So what we know here is that the initial velocity is completely horizontal. There's no vertical aspect, and that's equal to the final horizontal velocity, and we know that uv equals 0. A equals minus 10 meters per second squared, 9.8 everywhere else in the world, but Victoria it's minus 10. And then we substitute into our equations in order to solve. So we've got things like, if we want to solve the height, it's going to equal UHT plus a half AT squared. So if we want to use this equation, then we've got, if we're looking horizontally, like I'll put UH there, there is no acceleration in the horizontal direction. So if we're looking at horizontal, no acceleration. If we're in the vertical, then we've got UVT plus a half AT squared. Then there is 0 for your initial velocity. And so it's just like dropping it off a bridge. So you'd solve using that equation. Those are probably the most common equations you're going to use for that style of question, because you'll be given some information like the range, or you'll have to find the range, or find the height of the bridge, or find the time of the flight given how high it launched from, that sort of thing. So most commonly you'll end up using delta x as your starting point for this problem. Okay, second form is oblique projection. And that's where it's launched on the angle, and we get that parabolic path. So it's launched with some initial velocity u. So we've got UH equals, at an angle theta, UH equals U cos theta, and that will also equal VH because there's no acceleration in the horizontal. And we've got U vertical is U sine theta. If it's landing at the same height, then that's going to equal the negative of V in the vertical direction. Common things that we're going to look for in this one would be things like peak height. At the peak height, UV equals 0, or VV, if we're working our way up to the peak. And you'd use that where we've got V squared equals U squared plus 2AX. And then we can cancel that out using our initial velocity to work out its height. If we want time of flight, then it's 2 times the time to the peak. And the third scenario is oblique off a cliff. So we're kind of incorporating both bits from the previous scenario. So something like this, launched on an angle to the horizontal, and it goes out and hits some boat out in the sea. Alright, so again, same deal with initial and final, initial horizontal velocity, U cos theta, and U vertical is U sine theta. Final horizontal velocity were the same because there's no acceleration. However, this does not equal the negative of the final velocity, because it's now got acceleration under gravity all the way down below that cliff. Generally, I find it easiest if we work with delta x equals 0 at our launch site. Then our height, our impact height is negative, and our peak height is positive. I think it leads to less errors and less confusion when you're trying to work it out and solve your problem. Okay, so maybe we'll just go through a couple of examples, one for each. So let's make a scenario. We've got horizontal projection. Let's launch this off at 4 meters per second. Let's make our height 35 meters. And maybe let's start by solving time of flight. So what we know is UV equals 0, A equals negative 10. We know X will be negative 35. T is what we want. So looking at that, and as I suggested before, delta x equals UVT plus a half AT squared. Has all those four variables in it. That one's 0. So T will equal 2 delta x over A, and take the square root. Obviously, when you take a square root, you've got a plus or minus, but negative time would make no sense. So we've got square root of negative 70 over negative 10, which is root 7, which is, I don't know, 2 point something. 2 point something. Okay, from there, if I wanted to then work out the range, delta xh equals UHT, which would be 4 times root 7. Use the value that you calculated, the exact value, rather than the rounded answer you gave in the question before. Avoid carrying on rounded errors, which will multiply the more you use them. What if I want to work out the impact velocity? We now know the time of flight, so you can do V equals U plus AT, which is 0 plus negative 10 times root 7, which is negative 10 root 7. So we now have the details. We know it was 4 across, not to scale, and 10 root 7 down, which gives us our impact velocity V, and we need an angle to the horizontal, which is the same as that angle there. So you can use tan, theta is tan, or inverse tan of 10 root 7 over 4, and V would be the square root using Pythagoras' theorem, 4 squared plus 10 root 7 all squared. Punch that in your calculator, you got your answers. Notice there's that exact value used in each of those calculations. So oblique, let's launch at 30. So first things we want to do is we want to know what our velocities are. So UV is, say we launch that at 30 degrees, would be 30 sine 30. Sine 30 is a half, making that 15 meters per second as our vertical component. Horizontal component, 30 cos 30, which would be 15 root 3, since cos 30 is root 3 on 2. Once we've got that, we can then substitute that in. If we want to do time of flight, you can either find it to the peak height and double it. I prefer to use vertical equals 15. VV will be negative 15. A equals negative 10. T, we substitute in minus 15 equals 15 minus 10T. So we end up with time of flight is going to be, rearranging, 30 divided by 10, 3 seconds. What if we want to know peak height then? Once you know time, everything else is much easier. Peak height, you can use delta x equals UVT plus a half AT squared. You can also use V squared equals U squared plus 2AX, where V would be 0. So you can use X equal to U squared over negative 2A. Either of those options become available to you because you've got that extra variable that you now know. Range becomes UH times time of flight, which we said was 15 root 3 times 3, which is 45 root 3. And we're in metres, of course. Okay, and then the most complicated one that you could expect to see would be projection off a cliff at an angle. So let's make that 40. Let's work with the angle 30 degrees again, just because that makes it nice and easy. And let's go a cliff height of 50. Okay, UH is going to be 40 cos 30, which will be 20 root 3, and UV will be 40 sine 30, which will be 20 metres per second. So that's up, that's across. Okay, if we want peak height, be pretty common. You got to use UV equal to 20. We want VV equal to 0. A equal to negative 10. X is what we're after. So given that information, obvious equation is V squared equals U squared plus 2AX. X equals U squared over negative 2A, which is 20 squared over negative 20, giving us X equal to 20. Now, is that the actual peak height? Okay, so that's the peak height above our launching point. If it's the height above the if the question asks for the height above the water or the whatever's below, then yes, you need to say height above water is 20 plus 50, which would be 70 metres. Okay, time of flight. This is the most difficult bit in any of these questions, I think, because we've got to do time of flight. You've got to go stage 1 up to the peak, and then stage 2 from that peak down to the water. So we break it up into 2 sections. So I would look at this as UV equal to 0, UV equal to 20, VV equal to 0, A is negative 10, T is not sure, so we're going to solve. T equals V minus U over A, which is 20 on 10. So that's going to be 2 seconds to the peak. The other one, we've got UV equals 0, A equal to negative 10, T is we're not sure. What other value do we have? We don't have VV, so how do you solve that? Can't use the same equation. Do we know anything about delta X? We don't have to solve this by finding the final velocity. You can do it without that. Which we just did in that previous question, yep. So it's going to land 70 metres below here. So we've got to treat that as our new starting point. So negative 70 metres. So you can now say delta X equals UVT plus a half AT squared. That's 0. So T is square root of 2 delta X over A, which will be square root of 140 over 10, or negative on negative, which will be equal to the root 14. Root 14 is between root 9 and root 16, so between 3 and 4, close to 4, so we're looking somewhere around maybe 3.7, 3.8, so that when we're doing it in our calculator, think through, does your answer make sense? Forces. So starting this off, we had Newton's 3 laws. So first law, every action has object at rest or in constant motion will remain that way unless acted on by a non-zero net force. The area or the key word we're looking for here is constant motion. This is where it's going to appear in your exam questions. A car's moving at constant motion. What's the net force? Okay, constant motion, F net equals 0. There may be individual forces acting, but the net force is 0. I've seen that given as a 1-mark question, and people go, oh, I don't have the information to solve the question. Okay, the constant motion tells us net force equals 0. Okay, number 2, we've got F equals ma, or F net equals mass times acceleration. If there's no acceleration, then it's constant motion. However, when there is acceleration, then that becomes our net force that we're analysing based on its acceleration. The area that you're most likely, you may get the simple question of calculate the force acting when this object's undergoing a bit of acceleration, but the place you're most likely to see this is when we've got, the question like there's a car pulling a trailer or a train towing 2 carriages, and we need to then determine the tension. We need to then look at the forces that are acting. There's air resistance or drag on the trailer. There's air resistance or drag on the car. Then we've also got tension acting on the trailer. So this is the sort of question that you're going to need to analyse one component at a time. So analyse one part at a time. In this case, F net, if it's in constant motion, F net always equals the sum of the forces, the individual forces. So at constant velocity, then F net will equal 0. And that equals, I'm not going to equal force, it's going to equal tension. Scribble that out. Tension minus the drag that's acting on it. So in effect we're saying if it's in constant velocity, F net is 0, so your tension and your force are going to be equal. If it's accelerating, then the mass of the trailer times the rate of acceleration will equal the tension minus the drag acting on it. You expect, if it's accelerating, that it's going to be putting more tension on the trailer. So T equals ma plus the drag. And then once you've calculated that, you can then go on and analyse the car. So for the car, we've got, if we look at that car there, we're going to have the drag on the car and the tension both acting against it. So F net, we're going to be needing a driving force. Would be the driving force minus the tension minus the drag on the car, which should be F2. So when it's in constant motion, all those forces must equal the driving force. If it's accelerating, the driving force has to be greater to give it a greater force acting, in this case, to the right. And then the third law, every action has an equal and opposite reaction. Most common place that we see this come up would be as a normal reaction force. looking at an inclined plane. So here we've got some object on an inclined plane, angle theta. So we've got a normal reaction force here, and then we've got a weight force at an angle, mg. So we need to break up the weight force into components that align with the normal reaction force and the slope. So over here, we're going to have the normal reaction force equal to, the value of this here would be mg cos theta, and the bit acting down the slope will be mg sine theta. So the normal reaction force equals mg cos theta. Force down the slope, or resultant force, F net, would be mg sine theta. So unless there is a frictional force acting, then it's going to begin sliding down the slope. The acceleration down the slope would be g sine theta. F net equals ma, cancel out our m's, we get g sine theta. Okay, if you can't remember which way to go with your sines and your coses, really small diagram on your cheat sheet. Okay, momentum and impulse. Okay, mostly Unit 2 stuff that was reviewed here, with a couple of exceptions. So momentum, P equals mv, and then impulse, change in momentum, which could be m delta v, change in the velocity that's occurred, or it can also be calculated using the force times the change in time taken for that force to occur. So that last one leads us to another way to find it, is area under the force time graph. Okay, so commonly you'd get something like force applied, say a golf ball's been hit, it's not constant force, the area under the graph will be your impulse. After that, we then looked at collisions. So we have the sum of the momentum initially, or before the collision, must be equal to the sum of the momentum afterwards. Or if we want to substitute in, then it's just going to be the individual momentums or momenta for each of the objects. So for object 1 plus object 2 plus however many objects there are, must equal the final momentum, sum of the final momenta for each of the components. The first probably major variation or addition that really gets added here in Unit 3 is the concept of an elastic collision. And probably all too often in the questions, when you're asked in an exam, is the collision elastic, people show the final momentum and the initial momentum are the same and say therefore it's elastic. Okay? That has to, because momentum needs to be conserved. What we need to look at is the sum of the kinetic energy initially versus the sum of the kinetic energy finally. So if I got given that question on my exam, how would I answer that? I'd do EKI equals and do my calculation to get my final value in joules. I'd say EK final equals add up each of your individual kinetic energies, give your answer in joules, and then your overall statement. Therefore, and you've got one of two options, EKI equals EKF, therefore it is an elastic collision, or EKI does not equal EKF, therefore collision is inelastic. So work, power and energy. Work, power, energy, and their interrelationship. So work we defined as force times distance, Fx, and energy was the ability to do work. Okay, if the force is acting at an angle, such as something being dragged over a slope on the angle theta, then you would have to add cos theta in. Okay, it is measured in joules, and F is parallel to direction of travel. Power equals rate of work done. So we're talking work over time. Anytime you see rate, we're talking how long it takes to do something. So this is in joules per second or watts. All right, energy. Transferred or transformed, key concept. Okay, we're even going to highlight that. That's how exciting that one is. The reason that I highlight and emphasize that is that all your energy questions, if you don't realize that we're going from elastic potential energy to kinetic energy, from kinetic energy to gravitational potential energy, and backwards and forwards, you're either going to take a long time to solve the problem, or you won't be able to solve it because you haven't made that link. So anytime energy is mentioned in a question, think about what transformation's happening, and that's going to set you up to actually answer your question correctly. Okay, so you know, energy is transferred. For example, it falls, then UG becomes EK. So UG loss equals EK gain. Once you know that, because you may need to find the impact velocity, once you know that, if you knew the potential energy to start with, you know how much kinetic energy it's got right before it hits the ground. If you know that, it's half mv squared, you can solve. So maybe just recap, EK equals a half mv squared. UG is mgh. And US is a half kx squared. This is for, I've forgotten the word. Anyway, where we have a spring with a constant, a spring constant, or a half fx, because work equals kx when we're talking spring potential energy. So that is also area under fx graph, which is where that equation comes from. Now, important to note, x equals change in spring length. It's not the actual length of the spring, it's how much that spring changes by. So sometimes you will get given in your question that the spring, you'll get given the overall lengths and you've actually got to calculate the change in its length. So beware of that one. Okay, finally, no, not finally, we've got two things to go. Uniform circular motion. This is probably the hardest one for us to grasp first up. So uniform circular motion. Initially looked at just in the horizontal. And here we made or defined our equations that we're going to use. So we had V equals 2 pi r over t, where t is the period in seconds. Oh, what's going on there? And really all that is just distance over time. We're travelling in a circular path. A equals V squared on r, which is 4 pi squared r over t. And finally, the forces, F equals ma, which would then be mv squared over r, which is 4m pi squared r over t. Where do A and F always act? Always to centre. Otherwise it will stop moving in a circle. Okay, so one was horizontal. Two was where we termed it using aspects. So this is breaking it up when it's on maybe a string or something and it's at an angle to the horizontal, angle theta. So we've got mg playing a part, we've got fc, and the tension in the string, for example, is what's actually going to cause the circular motion. So you've got, you'd have T cos theta causes the centripetal force, and T sine theta is equal to the weight force. So often we may know the weight or the mass, and the mass allows us to work out what the tension would be. Once we know the tension, then we can calculate the centripetal force. So it's usually a couple of steps in that style of question. Less commonly asked than it is for the vertical plane, so motion in the vertical plane. So let's have a look at that. So, vertical plane. The good thing is we only need to worry about top or the bottom of the cycle. So often we'll get asked a question about maybe a roller coaster or a car coming down, doing a loop-the-loop, motorbike doing a loop-the-loop, or going over a speed hump or through a circular dip. So all we need to do is analyse the vertical forces that are acting. And really what we're looking at is the centripetal force is the net force. So we're either considering plus or minus mg, depending on whether gravity is helping with the turn or it's hindering the turn. And then we're either going to add or subtract the tension or the normal reaction force. So pretty much we've got two forces that we need to account for, and I guess just look at that and say, does it help the motion, the circular motion, or does it hinder the motion? Okay, so maybe let's look at a string first. So at the top of a circle, you've got tension acting down, and you've also got mg acting down. So the centripetal force must equal tension plus mg. Both of them are helping with the motion. At the bottom of the loop, tension acts up, mg still acts down, so F net, or your centripetal force, is T minus mg. There's no real hard and fast rule, we've just got to look at it case by case. So drawing a picture or drawing on their diagram will often help with this. So next would be something like a car going over a gigantic speed hump. Whoops, car's not even on the ground. What a good looking car. We're airborne. So pretending that was actually on the ground, we've got mg acting down, and you've got your normal reaction force pushing the car up. So here, Fc equals mg minus the normal reaction force. The common question that would come up with this is Vmax to not get airborne. Okay, if it goes too fast, then we're going to get airborne. You'll have zero normal reaction force. So you'd say, you'd be looking at something like mv squared on r equal to mg to solve it. M's are going to cancel out. Rearranging, you're going to get v equals the square root of rg. That's to work out the maximum velocity that it can go over that section of road. Fairly common question to see. The alternate to that is looking at the bottom of the loop, when we get our car, bottom of the loop. And here we've got mg acting away. Normal reaction force is actually helping. So at the bottom of this scenario, centripetal force would be normal reaction force minus mg. Normal reaction force must be greater than the weight force. So this is like when you go through that dip, it feels like you're being squashed down into the bottom of the car. And when you're going over the top of the hill, it actually feels like your stomach's rising up in you, and you sort of get that, oh, I feel really light, roller coaster type feel. Okay, the third scenario that you can possibly get would be the roller coaster type deal. We've got the big loop-the-loop, and in this case, roller coaster car, we've got mg down. We also have the normal reaction force acting down. So here Fc would equal mg plus n. And the common question that you would see here, much like we had in the going over the top of the hill, would be the minimum speed to actually make it round the path. So here you've got, at a minimum speed, you would have Fc just equal to mg. At the minimum speed, there'd be no normal reaction. So same as before, mv squared on r equals mg. Cancelling that out, you're going to rearrange to v equals square root of rg. Same equation, different scenario, gives us minimum speed in this instance, maximum speed over the top of the hill. Okay, and then the other situation at the bottom of this roller coaster, still on our circular path, of course, kind of not really drawn that very well. Got normal reaction force up, got mg down, so your centripetal force is n minus mg. If you're or I have seen it in a question in the past where they start at the top of a big ramp and then come down, do the loop. They link all the energy questions into the centripetal motion questions. So you start off with a conversion from elastic potential energy to kinetic energy, and then do the loop, and then analysing loss in energy as it goes back up in a height to the top of that circle. So just, beware, think energy anytime there's variation in height. So the last thing is linking gravity and satellites. So universal law of gravitation, F equals G M1 M2 over R squared. So G is something you're going to grab from your data sheet. I don't remember what it is. I don't need to remember it because it's on your data sheet. It's given to you in your exam. R is the distance between the two centres. It's going to be in metres because we always have it in all our units in metres. Substitute in your masses to work out that force of attraction. Gravitational field strength, that is where we want to work out G at any given height above Earth, or G at the surface of some planet given some of the information. Then really what we're saying is F equals ma, where a is our acceleration due to gravity. So dividing by m of the object that's going to undergo acceleration, so the object, the ball that's going to experience acceleration on the surface of the planet, becomes g m over r squared, where that's the large mass. So typically this would be find the gravitational field 500 kilometres above the surface of the Earth. So you've got to add the radius of the Earth to your height above, make sure it's all in metres. That's fairly typical use of that equation. So satellites. Generally, we're looking at those that are following a circular path. So we basically link this into uniform circular motion. So you've got V equals 2 pi r on t still. We get A equal to V squared on r, which is 4m pi r squared on t, which also equals gm over r squared. So you may need to rearrange different equations based on the information you're given, and of course F equals ma mv squared on r, oops, that shouldn't have an m in there, for m pi squared, pi, it should be squared, shouldn't it, pi squared r, got that all wrong, pi squared r over t squared, got that completely wrong, which is gmm on r squared. Does that mean I did that wrong on the other? Let's have a look. I did get that. I missed the t squared there, guys. So make sure you do fix that up on yours. And that probably just highlights how easily or how common that mistake is, where they'll even write it on the equation and then forget to do it as they substitute in. So the little squareds, so many errors, careless errors happen forgetting to square something. Something that's probably not strictly in the course is Kepler's third law, but that is a rearrangement of these last two equations. Putting that on your cheat sheet can save you time and effort in your exam. So we've got Kepler's third law. Rearranging this one here, we get r cubed on t squared equals gm over 4 pi squared, which is constant. So everything on the right-hand side is a constant, so that makes that whole right-hand side a constant. So that means any object orbiting at a given height, the ratio of the radius cubed over the period squared will create a constant. So if you know for two different objects in orbit, if you know the radius for both and the period for one, you can calculate the period for the other because they will equal a constant. Or you could rewrite that as r1 cubed on t1 squared equals r2 cubed on t2 squared. So that's a little bit of an extension on that, but it can come up and they would expect you to go through the process of, I guess, coming up with that equation on your own by rearranging the force equations. So having that there can save you time. Final thing was energy changes in gravity fields. Okay, this is another one. Once we're in this energy field, the word energy, we're looking at change in kinetic energy. So gain in kinetic energy is going to come from gravitational loss. So if an object drops height in a gravitational field, it's going to increase in its velocity and therefore its kinetic energy. And of course, vice versa. If an object goes higher in that gravitational field, it gets greater gravitational potential energy, but it's going to come at the cost of a loss of kinetic energy. Typically, questions around this come with a graph where we've got the force acting on the object. That's going to be in newtons for the given height or the radius of the orbit in meters. So here is one of those ones where we want to look at area under the graph. It's a counting the squares exercise normally. Count the squares, multiply it by the values or value of one square, what one square would be worth. So area under G equals Fx, force times distance. That's the work done. And therefore, that's the change in EK or the change in UG. The other, I guess, the variation of that is where they'll give you G. And they'll give us the radius in meters. This would be in meters per second squared. The graph looks identical. You still do that. But what that gives you is gives you the, I suppose, the work per kilogram. So you have to multiply that by the mass in order to convert that into a work graph. Right, probably the other thing we might just mention was for objects in free fall. They are accelerating at G. Therefore, they experience apparent weightlessness. And that's because they and the object are both accelerating down at the same rate. So a normal reaction force is not possible. That's why you see astronauts that are in orbit appear to just be floating in there, because both the shuttle that they're in and the astronaut are falling towards the Earth. All right, that's it in a nutshell. We'll hold it there.